Hello, I'm Pablo Gómez Abajo. Today I'm going to present our work, Systematic Engineering of Mutation Operators. I've done this work with Esther Guerra, Juan de Lara and Mercedes Merallo. Firstly, I would like to introduce this presentation explaining what model mutation is. A model mutation is a variation of one or more seed models by the application of one or more mutation operators. This process generates a set of mutant models as a result, which contain these variations. Model mutation has many applications, such as model transformation testing, software product lines testing, search-based engineering, the automatic generation of exercises, and model-based software mutation testing, among others. We can see at the bottom of this slide an example of a mutation operator applied to the domain of innate automata. In this case, the input of the process is the seed model placed on the left of the figure, which corresponds to a finite automaton that accepts the event binary numbers. The applied mutation operator, in this case, swaps the symbol of two transitions. Here we can see two of the generated mutants with these variations presented in red color. So in this case, the symbols of these two transitions have been swapped. The resulting mutant models may accept a different language from the one accepted by the seed model. On the right side of the slide, we can see another example. In this case, it corresponds to the application of a mutation operator to the domain of a programming language. In this example, the applied mutation operator replaces an equals operator of a conditional by a distinct operator. Well, the problem we face here and the problem that motivates this work is that there is a need to define mutation operators using a simple and compact notation, not the more common general-purpose language, which is usually error-prone and incurs in high costs when we use it with this target. This language tailored to mutation would enable changing the artifacts in pertinent ways and would allow testing the mutation operators in an easier way too. With this purpose, we have created a DSL for model mutation that we have called Wodel. This DSL allows synthesizing models from the Wodel programs, testing the mutation operators over them, and presenting a set of mutation footprints which show the mutation coverage of the meta model. Here we can see the complete process of our proposal for the engineering of mutation operators. This methodology is independent of the kind of the artifact to be mutated, as the artifacts that we are using are models. In step 1, the engineer defines the mutation operators, which are coded in the Wodel DSL. In step 2, the engineer validates the defined mutation operators by executing them over test models, which may lead to detect possible errors in these operators implementation. This is the step where the seed model synthesis takes place. In step 3, the engineer assesses whether more mutation operators are needed. For this purpose, we provide a detailed indication of the degree of coverage of the meta-model by these operators. If this coverage is insufficient, then in step 4, the engineer can use the provided mutation operator synthesizer to automatically generate new operators that increase this coverage. Then the engineer can iterate this process until the mutation operator set is complete. Well, these are the main features provided by our DSL Wodel for model mutation. This DSL has high-level mutation primitives, it is domain independent, and it is automatically compiled to Java code. The Wodel tool provides a set of extensible execution services, such as the mutant validation, the possibility to specify an equivalent mutant detection criteria, a registry of the applied mutation operators, and it is extensible for post-processing applications. The Wodel tool provides these two development services, the seed model synthesis from the Wodel program, and a collection of mutation footprints, which is the visualization of the mutation coverage of the meta-model. Well, in this slide we can see at the bottom a simple example of a Wodel program applied to a simplified UML class diagram meta model that is presented here in the center of the slide. The simplified UML class diagram meta model contains the main concepts of the language, such as classes, relations, attributes, and operators. It also contains an OCL constraint, which requires that a class cannot be inherited by itself. At the bottom of the slide, it is presented this example of a simple Wodel program. A Wodel program has two parts. The first two lines correspond to the configuration of the Wodel program. In this case, it specifies that the mutants are going to be generated in an exhaustive mode. That means that all the possible mutants for the given operators will be generated. Wodel provides another mode to generate the mutants, which is the stochastic mode, that generates the mutants randomly. These mutant models will be stored in the out folder, and the set of seed models will be loaded from the models folder. In the second line, we specify the domain meta model that we are using. In this case, it is the simplified UML class diagram meta model shown here. The second part of the Wodel program corresponds to the mutation operators that are going to be applied. In this case, we have included here only one mutation operator, which retypes a relation that can be of types aggregation, association, or composition by a relation of a different type. We can see in this slide an example of the application of this mutation operator, which retypes a relation. This seed model presented here describes a UML class diagram for vehicles. A vehicle has a brand and a price and can be either a car or a truck. And also a vehicle can contain a set of wheels. When we applied this mutation operator that replaces the relation type by a different one, we can see in the generated mutant that this wheels composition relation has been replaced by an association relation with the same name. Well, the core of this work is a methodology for the systematic engineering of mutation operators. And the first service we provide with this purpose is this method, which is the testing of the Wodel programs, which is the seed model synthesis. This seed model synthesis method we propose is based on model finding. This method automatically produces seed models over which all the instructions of the given Wodel program are applicable if such models exist in the given search scope. This figure shows the seed model synthesis process. It is based in model search, which is a technique that applies constraint resolution over models. The model synthesizer enriches the domain meta model and its OCL constraints with additional OCL invariants derived from the Wodel program. These additional OCL constraints correspond to the requirements that a seed model must fulfill to allow the application of the mutation operators included in the Wodel program. The enriched meta model is then loaded into a model finder, which performs a bounded search of instances of the meta model which satisfy all these OCL constraints. If a model is found, then it is assured that all the Wodel program statements will apply over this generated model. In this slide, we present two templates used for these two Wodel mutation primitives, the object creation and the object deletion. The first column shows the conditions to check in natural language. The second column shows the OCL templates used in each case. And finally, the third column presents the corresponding OCL code generated for this simplified UML class diagram meta model example. The complete OCL templates table is included in the paper if you are interested in the rest of the OCL templates for the rest of the mutation operators. In the case of the object creation primitive, it is demanded that at least a container reference of the object's type has enough space to store the new object. The derived OCL constraint for the mutation operator create class for this UML class diagram metamodel example checks that there exists at least one class diagram object which has its class's reference with enough space to store the new object. That in this case means that its contained classes are fewer than its upper bound, that in this case is 10. In the case of the object deletion primitive, it demands the existence of an object with the specified type and feature values, and that it is also included in a container reference that would not violate its lower cardinality bound if the object deletion takes place. The derived OCL constraint for the mutation operator remove one class checks that at least one object of the type class belongs to the class diagram, and that this class diagram object contains other elements apart from the class to be removed. That means the size of the reference class diagram dot classes is greater than 1. That is its lower bound. When we delete this class object from this containing reference, its cardinality would still be satisfied. Here we present an example of the seed model synthesis, starting from the Wodel program that we are using in this presentation. This is the OCL, the derived OCL constraints from the Wodel program, that in this case require that the model contains at least one object of types aggregation, association, or composition. Then this OCL is loaded into the model finder along with the corresponding OCL of the UML class diagram meta model. And here we present an example of a generated model. This model has a composition object, thus this mutation operator will be applicable over this generated model. The second service provided by the Wodel tool to ease the mutation operator testing is a set of visual mutation footprints which show the mutation coverage of the metamodel elements. This set of mutation footprints consists of two kinds of footprints. First, the static footprints, which present the elements of the metamodel affected by the mutation operators, and these metrics are classified by the footprints for the complete metamodel or the footprints by each of the mutation operator. In the case of the dynamic footprints, they reflect the real effects of the mutation program over the generated mutants. These metrics are presented by the net footprints, which reflect the creation, modification, or deletion effects over the generated mutants, or by the debug footprints, which reflect as well the program's mutation operators which have been applied over the models but are not reflected in the resulting mutants. These debug footprints are interesting to check those mutation operators that have been cancelled during the mutation process. As an example, those cases where firstly we create an object and in the Wodel program we delete this created object. This will be reflected by the debug footprints. Okay, so here we present the tool support provided with all these features. Wodel is an open source tool provided as an Eclipse plugin, and it's available at this website along with videos, tutorials, and examples. This is the Wodel editor, which consists of a complete development environment with enhanced features like syntax highlight, code completion, automated Java code generation, among others. This is the Project Explorer with the set of Wodel programs the domain meta model and the seed models used in the example, and also the corresponding generated mutants, which are stored in hierarchical folders labeled with the name of each mutation operator. These are the set. These are the Eclipse views which present the resulting mutation static and dynamic footprints. And finally, here it is shown the mutation operator creation wizard. Well, now I'm going to play this short video demo that shows the seed model synthesis and the mutation footprints. This is the Wodel editor, which has code completion and syntax highlight. These are provided by the tool we used to create this DSL, that is xtest. These are the class elements of the UML class diagram meta model. These are the properties of the class object. And well, now we are going to present the meta model static footprints. Each element affected by the mutation operator is highlighted in color. These are the operator static footprints. For each of the mutation operator, it is presented which elements of the meta model are affected by each of them, these properties of each class, and Wodel also provides a graphical meta model static footprint. And well, now we are going to generate the seed model for this selected mutation operator. This is the .use enriched meta model code that we are going to load in the model finder, that in this case is the use model validator model finder. Now we are going to launch the seed model generation. It starts the seed model generation wizard, where we can include the features of this process. Now it's generating the seed models, and here we can see the generated seed model, which has a class object with its public visibility property set to public. Now we are applying the mutation operator, and these are the generated mutants. Now we can see that the generated mutants have the visibility property set to a different value from the one that was corresponding to the seed model. As we can see here, the mutation operator has been applied to the seed model and has generated 2 mutants, as it was expected. So now we can also take a view to the dynamic net footprints, which show the affected elements of the generated mutants. So for each of the generated mutants, we can see the affected properties, that in this case are the visibility property of the class object. Okay, so well, to end this presentation, we must mention here that we have presented our model-based approach to define a methodology supporting the integral engineering of mutation operators through their definition in the Wodel DSL, with the seed model synthesis and the mutation footprints. As a future work, we plan to generate near misses models, which will allow us to generate models where the operators are not applicable but are close to being applicable. And we also plan to generate models which ensure that the execution of the Wodel program will lead to a correct model. Well, many thanks for your attention.